Okay. Welcome to today's workshop. I'm Andy Lyons, and I'm excited to talk about computing agroclimate metrics in R. We've got the workshop website up. This is where we'll start. I presume everyone has at least had a look at this. Hopefully you've created an RStudio Cloud or Posit Cloud account. It's the same thing. They recently renamed themselves. So we'll just dive right in. So let me go into the first set of slides where I'll introduce myself and my team a little bit more. Okay, so for the next 90 minutes, we'll basically be going through some slide content and then go into the R notebooks back and forth. So a little bit about me. So I work for the UC Division of Ag and Natural Resources. In California, here in the US, this is the branch of the university system that provides the extension services to growers and land managers throughout the state of California. It's part of our land grant system. So we are part of the UC system, but we're not part of the campus system. Our researchers are scattered throughout the state of California, farm advisors in all of the county offices. We also have clusters of faculty on 5 of the 10 UC campuses right now. And there's also a bunch of statewide programs that have statewide coverage, some of which are very popular. Youth education, the 4-H program would be one of them, master gardeners, and so forth. I work with the Informatics and GIS group. We are a statewide program, and myself and my colleagues have the privilege of providing spatial technology and research support to this entire network of researchers. So this is my groups. We are a smallish team of GIS analysts, programmers, cartographers, spatial data scientists, drone pilots. And this is the kind of stuff we do. We have a fleet of drones that we do drone projects for researchers. We do all manner of GIS services, from making simple maps to crunching through spatial data to making web applications and mobile apps. We teach workshops such as this one, and we do office hours. So if you're in California or you're within A&R, please take advantage of us. And I will highlight, though, that our workshop hours are for everyone we interact with, including workshop alumni. So if you have any questions after today's workshop, feel free to sign up for office hours, and we'd like to keep talking to you more. And today I'm with Robert Johnson, Shane Fire, and Ben. These are some of my colleagues, and they will be providing support in the back end. Thank you, everyone, for being here. This workshop is new. This is the first time we're running through this, but this is part of a bigger stream of activities that my group is working on, myself primarily and Shane Fire, to develop more resources for building decision support tools using open source platforms. Not exclusively, but starting with open source platforms. So this has begun with, I've developed a number of R packages to provide some of the core libraries for working with these kinds of metrics in Python and R. We've also built a number of Shiny apps. Talk a little bit more about that coming up, but these are basically user-friendly web applications that can work on phones or browsers or tablets that make it allow you to share your R projects with anyone who has a web browser. So that's been a lot of fun. And most recently, we're trying to develop some outreach materials to reach not really growers or producers, but people who work with data scientists, grad students, who have the ability to work with these types of models for developing support for agriculture and natural resources. So this is part of a thread of work, and thank you for being kind of our guinea pigs. About the people who registered for this workshop, not a big surprise, mostly people from academic institutions, so that's wonderful. A handful of people from government agencies and other nonprofits in there. You want to see specifically what schools people are coming from here in California: Davis, Riverside, Berkeley, These are the big campuses with an A&R, with other colleagues, some colleagues from Germany. Welcome, everybody. I know it's very late for you there tonight. This is where people are scattered. So it's nice to see a nice metric here. We have some folks from North Africa, Tunisia, Algeria, Morocco, some people over in Bhutan, in India, and of course, a big cluster of people coming from California. And I know not everyone is here today, that's fine. A lot of people sign up for these things so they can catch the recording and get the emails. So background, a lot of people here are not too familiar with AgroClimate Metrics. I kind of put myself in that boat. This is a relatively new thing for me. I have a deep background in programming, but I'm learning as I go about how to make these tools useful for ag and natural resources. But we'll definitely cover an introduction to the types of metrics we're talking about here. And most people here have at least a bit of our experience. So that's good to see as well. And again, we'll be going through that a lot today. That's kind of the main goal. This is primarily an R workshop, even though we will be talking about the science. Okay, so what we'll be doing today, it's divided into two parts. We'll start out with a short presentation on AgroClimate metrics and the types of weather data that are out there, go through some R techniques that we'll begin using in the notebook. So we have two notebooks that we'll go through, and that's where we'll probably spend most of our time. Then we'll take a break, and then we'll come back and do a little bit more presentation on somewhat more advanced metrics that are a little more computationally complicated and use cumulations of the metrics to come up with decision support, and talk a little bit about how we can create those in R using specialized packages, as well as look at how you might summarize multiple years of data. And then we'll do another notebook. I initially had hoped to do a third part. This will have to wait. I don't think we'll have time for it today, but this is some of the other stuff that you can do. These same models work equally well with projected climate data. So if you're interested in what agriculture might look like in the future, this is a technique we'll use for that. But that'll have to be maybe the next version of this workshop. The goals here are basically to get everyone familiar or a little more familiar with what AgroClimate metrics are and why they're useful. Talk a little bit about weather data, the different types that are out there, how do you get to it, review how you work with these kinds of data in R. I mean, the essence of what we're doing today is working with weather data, which comes in as data frames, and then manipulating it within R to create these metrics. I mean, that's in essence, that's what it is. There are some specialized R packages that we'll look at. So my hope is 90 minutes, you'll come away with a little bit of hands-on experience if you choose to go walk through the notebooks with us. But more importantly, I want you to have working code recipes that you can come back to, because this is a niche topic. And unless you're probably not working on AgroClimate metrics this second, but hopefully in the coming weeks or months, when you do need to come back to this, you can go back to these notebooks, which are already chugged. They're linked to the homepage if you just want to see them. And then you can see some examples of how you work with these kinds of data in R. Here are the links to the workshop materials if you'd like to follow along. One thing I will highlight is everything that we're looking at here is on GitHub. So if you want to bookmark this or save a copy for posterity, you're welcome to do so. You might wait a week or so. I usually make some updates after about first go of a workshop. Okay, I'm going to keep my eye on the chat window. Please put a note in there if you have any questions. Otherwise, I'll keep going and I'll ask my colleagues also chime in if anything comes up. All right, let's talk a little bit about what are AgroClimate metrics. This is not a common term. It's a broad term. I might not be using it right. I do know we have some real experts here in the audience, so please chime in if I misspeak or gloss over important details. But I'm referring to AgroClimate metrics in broad terms as various weather-driven factors that influence the development of plants and insects. So they're really helpful in agriculture and natural resource management. If you hear some examples, many of these are pretty intuitive. You can more or less figure out what they refer to. But basically, weather-driven variables that are important for understanding how plants and insects develop. Because they are weather-driven factors, these are mostly abiotic factors, but that being said, they also have a role in biotic factors such as maybe disease or nutrients. Right? So, but they are essentially abiotic factors. That's what we're talking about here today. The ingredients that you go into computing these are primarily going to be measurements of weather, such as air temperature and precipitation and evapotranspiration. So it's things that weather stations pick up using sensors. But the cool thing about these metrics is because they are generic and they're based on plant physiology, insect physiology, you can chug them for past, present, or future data sets. So they're very handy for all kinds of questions as well as applied purposes. So let's talk about why they're useful. They're useful because they're good predictors of growth, and that is the essence of it. And that makes sense, right? Because plants and insects are cold-blooded. They are dependent on the ambient temperature for the metabolic rate, and the metabolic rate controls all kinds of development processes in phenology. So how these kinds of metrics are useful in ag operations. One is timing, for example, of pest management. So if you know, if these models tell you when the bugs are going to be buried inside the tree or buried inside the fruit, not very accessible, versus when they'll be eggs or flying around, it gives growers better ability to use the whole toolbox of pest management, including, sort of the biotic controls and mating disruption and cleaning up the orchard so the habitat for certain life stages gets affected. So the timing is everything in using these kinds of integrated pest management techniques, and ultimately that's going to save the grower money and it's going to reduce the harmful side effects of things like spraying. And if they do need to spray, that can be optimized. Other kind of scheduling is irrigation. That's important. California is a dry state. Everyone's trying to save water. So the more we can save irrigation by not overwatering is going to be beneficial. Some crops you can easily use deficit irrigation, save some water, don't affect the quality of the harvest and so forth. You can also use these metrics to tell you when it's time to go out and look for the bugs, for the pests that you're concerned about. For scheduling harvest, they can tell you when your nuts are going to be ready to take off the trees and so forth, and all other kinds of operations. And there's lots and lots of research that have shown how these metrics can actually predict what you might get for next year. All right, so farm operations is another use case. And then finally, a lot of researchers and a lot of people are interested in what the future looks like. We know climate change is very much with us. And these are some of the kinds of questions that have been asked in the recent years. Where could I go right now to see what my city is going to look like 50 years from now? So that's an example of a climate analog. How many generations of navel orange worms will growers in California have to deal with in the coming decades? That's based on one of these models. So you just run the model for projected climate data. How much chill might we expect from the coming decades? Is there going to be enough chill to have an economically viable farming operation? Again, is that based on chill portions? In fact, the author of this paper is with us today. So thank you for joining us, Ike. That's one of the earlier works that came across my radar screen, and so on and so forth. What all of these papers have in common is that under the hood, they're using these kinds of metrics to answer questions about what agriculture might look like in the coming decades, based at least on one aspect of climate change. The aspect that's most dominant, at least here in California, which is going to be the temperature change, but also extreme precipitation frequencies and so forth. So they're generally useful. Why might you want to work with these in R? Well, I probably don't have to tell this audience that R is a very, very flexible, powerful computing environment for working with data. It's very mature, very well developed. It's been largely developed by researchers, excellent for all kinds of data manipulations, the kinds of things we're doing today. There's great plotting and visualization packages. Any statistical modeling that you want to do under the sun. R is a great environment to either apply something that's been developed or come up with your own. You can easily integrate other kinds of data. It's widely taught in ecology and the biological sciences, and there's a very strong user community. Thousands and thousands of users have contributed packages. And some of those packages are for accessing weather data. So it's getting easier. I wouldn't say it's easy, but it's getting easier to import weather data into R through packages like these, through APIs. This is just some of them. But this, if the weather source that you can use is available through an R package, then it saves you the pain or the effort of going to someplace and downloading large TIFF files or large CSV files and importing them through a manual process. So we're seeing it's getting a lot easier. It's actually not that hard to write your own code that downloads data from a weather provider, given that you have access to it. And then finally, Shiny is an R package, and this has really been a game changer because this allows you to build interactive websites that under the hood are running R, and this has made it possible for researchers to relatively quickly come up with little decision support tools and get them out to their audience. You don't have to be a web application developer. It still takes some knowledge, but it really lowers the bar to making these kinds of applications. All right, so R is a great tool to work with this stuff. Okay, let's talk a little bit about weather data. Questions? So there's generally the best quality of weather data for agricultural applications are going to be sensors that are mounted on weather stations. And that's still the standard for these kinds of work. The good news is that there are lots of these networks out there. A lot of private networks are popping up. This stuff is becoming affordable. Many of these data providers are online, or they provide their data online. We'll talk a little bit about what that looks like in a bit. So that makes it easier to get it. There's lots and lots of details about good weather data for modeling crops and pest development. Obviously, if the weather station is close or on site, that's going to be preferable than farther away. You want weather stations that are on the ground. A lot of times, the airport sensors may be on top of the building or out on a runway. So there's a lot of details like that about what is good weather data for agriculture. But the good news is there's a lot more options out there. And these are the kinds of sensors that these stations typically have. And so it's a lot more than just temperature and rainfall. You can see there's a whole bunch of stuff here. Today, we're primarily going to be talking about temperature for our examples. Okay, so that's where most weather data starts from. There is satellite-based weather data. I'm not going to talk about that. That's a different kind of thing, and it doesn't apply as much to ag. It's a different kind of data, but there also are interpolated and gridded weather data sets. And these are basically that same set of weather stations that they then apply modeling to fill in the gaps between the stations. Here in the US, some common gridded weather data sources include PRISM. gridMET is based on PRISM with some additional regional downscaling and libnate. So anyway, these are just some of the ones that I'm familiar with. There's others out there as well. So how do you get to weather data once you find somebody that's providing it out there? There's generally two ways to digitally get weather data, or two broad buckets. One might be where you have to go to a file server, might be an FTP site, might be an HTTP site, looks like this. And there's your files. And you basically have to download the file for the time period and the area that you're interested in, and then work with it once you get it. All right. The disadvantages here is that these files might be really large. Like I know a lot of the ones I just mentioned, the files are in states. There's very few people in ag who are really need such a large area, but that's what you get. And they can be large files. You can see the file sizes here. many, many megabytes. And then you have to work for them themselves. So a lot of weather providers, a lot of the public ones that aren't charging anything, that's what you get. But more and more, we also seeing weather data providers providing an API service. And this is an API, it's basically like a translator for computers to talk to each other. And it allows a client, such as your laptop or your server, to communicate with a weather provider database and send commands so you just get just the dates you need, just the variables you need, just the location you need. So this makes life a lot easier. There's more expense and cost in supporting these kinds of things. So you may need to register, you may need to pay a subscription. But more and more the public services are also providing API services because there's such good demand. All right. So, okay, so let's talk a little bit about R and R techniques that we're going to be using in a few minutes to actually work with some of these data. So this should mostly review, I hope, for most people if you worked with R recently. But piping is one thing we're going to be working with a lot in our notebooks. Piping, it's just a way of writing expressions. So here's an awful looking expression with lots of nested parentheses. If you've ever suffered in Excel, that you have to, if you get one parentheses wrong, things go off the rails. Piping is a way of chaining together functions in R using pipe operators. So you're writing something that looks more like a sentence than lots of nested parentheses. And under the hood, basically what's going on. So this is the pipe operator. There's two pipe operators that are widely used today. This one, which is the pipe, and then the greater than sign, is newish to R, 4.0. The other one I've highlighted here is a more traditional, older one based on the Madrida package. But basically, both of these will take the one expression and then feed it to the next expression as the first argument, and so on and so forth. So instead of so when it's done, you get an expression which is much easier to read. That's the essence of it, right? I suspect this is not, most people who have worked with R have seen this before. An RStudio keyboard shortcut is Control-Shift-M, and you can specify which pipe operator you want to bind to that keyboard shortcut under the global options. Okay, so we're going to see piping. We're also going to be doing mostly data wrangling, and that's a broad term that refers to all kinds of operations that you're going to be working on a data frame. Changing the columns, dropping them, renaming them, reordering them, a lot of row filtering and row sorting. We'll be doing that. Creating new columns based on some kind of function or expression. That's a standard practice in a lot of data wrangling, reshaping data, and so on and so forth. We'll mostly be doing the stuff that we're going to see here in the first column. The good news, though, is that R has a really good, popular, well-developed package called dplyr. It's part of the Tidyverse family of packages. It has lots of functions that are designed specifically for this kind of stuff. I'm a big fan of cheat sheets. If this is newish to you, you might want to click on this cheat sheet later and check out some of the functions. These are the ones that will probably do like 90% of what you need to do with data frames in most use cases. And these are the ones that we'll be looking today. So in different orders, you mix and match these in different ways, and you can get lots and lots of stuff done with dplyr. So the nice thing about these data wrangling functions from dplyr is that for the most part, they all expect a tibble as the first argument, and they return a tibble. So that makes them very pipe friendly, right? So hence the piping comes back in. So to see an example of that, here's a little data frame that comes with dplyr, and here's a data wrangling expression. And as you can see, it's just a bunch of those functions that are chained together with these pipes, and it's okay to split them across rows. And you can see what each one does, with, I'm not going to read through all of these, but it makes it relatively easy and quick to read and write these kinds of expressions, right? We'll be doing a lot of this in our. All right, so that's a little review of data wrangling. Another data operation that we'll be doing today is changing the shape of the data. This is also called pivot tables or crosstab queries, and it's basically changing the structure of your data frame from back and forth between long formats and wide formats. And we'll see examples of this. So I'm not going to go into the details right now, but a lot of times you might get, actually you can get weather data back in either long or wide formats. So it's important to be able to go back and forth because some of the functions that you're going to be wanting to use will expect long data or vice versa. So being able to go back and forth between long and wide formats is a really important skill, and you can do, these two functions are very well developed and they've got tons of arguments to do that stuff. The last little trick on kind of working with the data that I'll review quickly is how to handle data, because that's obviously going to be part of the kind of data that we have to work with. A lot of times what you might get back from your weather data will be date values written as text. So that needs to be converted to date objects in R. And if it's well formatted text, and it usually is, you can just use as.date, and then you get a date object. And the reason you want that date object is then you can sort on it, you can filter it, you can group by it, you can get the date parts. It's really important to get your dates turned into date objects. That's like step number one. The LubriDate package has lots and lots of functions that can help you, whatever format your data comes in, if it's in separate columns or in some strange format, you can probably use the LubriDate function to get it into one of those data objects. And time object. Okay, and then finally, before we go to the notebook, we're going to be using ggplot. ggplot is a very powerful and common plotting package for R. You've probably seen it before. And here's a typical plot statement using ggplot that makes this little scatter plot, right? So as you can see, it always generally starts with ggplot, and then there's some other functions that follow it to produce your little plot. So depending what functions you put in, you get lots and lots of really nice looking plots. There's lots and lots of galleries. So, but let's quickly talk about the anatomy of a ggplot statement. Hopefully this will help you follow what we're going to see in a few minutes. So ggplots are generally constructed by adding a series of functions together, not using the pipes, but using the plus signs. So that's worth taking a note. The first function is always going to be ggplot. And this is kind of like sets up a canvas for your plot. All right, that's basically what it does, as well as creates a few defaults. The first argument to ggplot should be a data frame. ggplot wants a data frame. If your data are in different vectors, you need to push them together into a data frame. It could be a spatial feature data frame if you're working with map data, but you want to give it a data frame. And then the second important argument, which is not always intuitive to that ggplot function that sets up the defaults for your canvas, is a mapping object that you create with this AES function. And this basically maps or tells it which the columns of the data frame, how should they be used in the subsequent functions that draw things. So for example, there's a function, there's a column in this data frame called flipper length, and we're saying it, if nothing else changes, when we have a function that draws something, it should use this column for the x-axis, and so on and so forth. Many of the functions that draw things can also specify, the color or the line thickness or other attributes. And you can also set defaults sources for those attributes in your opening ggplot. And then you'll have one or more functions that actually draw things. Those are the ones that actually put things on the canvas. Most of them start with geom, but there are others as well. And then at the end or at some point, there's lots and lots of other functions you can do to change the plot as a whole or set options and so forth. But that's the structure of it, right? So we'll see examples of this. Okay, no questions so far. So let me talk a little bit about our notebooks in case this is new for you. I like using R notebooks. It's a form of R Markdown. I use them. I don't use them in my day-to-day work, but they are nice for workshops. If you haven't worked with them before, they're fairly intuitive. It's a plain text file, so it's a lot like an R script. The top bit of it is called the header or the YAML header. This is just leave it alone. Don't muck with it. It kind of specs some options for this notebook file. You'll see a lot of the formatting when this gets saved. The HTML is generated with things like the hash or pound character. We'll turn things into headings. You can make things italics and so forth. So you see a lot of that formatting stuff in your Markdown document. And the R code that actually has to be written properly and actually runs when you render the notebook is the stuff that's in these little code chunks. Right? So, and they're, again, manually written. If you want to, if you're working in an R notebook, you can just click in a code chunk, and to run one of the lines, you can put the, you can click that little run button. There's another, you can also hit Control Shift. And then there are other buttons you can use to run other code chunks. By default, when you run code chunks, the output appears not in the console or not in the plot window, but underneath the code chunk inline. So that throws some people off. You can change where the output of your code chunks appears under the settings option. And the cool thing though is like when all is said and done, every time you hit save, it's going to render in the background an HTML copy of your notebook, as well as the code chunks that you've run, and save it as HTML. And then you can keep that HTML. You can open it in a browser, and all of the code that you've run is there. So that's what we'll be using today. Okay, so let's go into our studio. We're ready for our first notebook, and I don't see any questions. I'm going to assume things are going okay for people. Go ahead, I'll put this link in the chat window. Hopefully you've already, I'm assuming everyone has created a RStudio Cloud account or Posit Cloud account. Click on that link in the chat window if you have not already. I'm going to do it right here. And that will open up Posit Cloud, and it will open up a copy of this RStudio project. And the first thing you should do once it opens, you may have to log into Posit Cloud if you're not already logged in. Once the project opens, go ahead and click the Save a Permanent Copy button. Right? That will make a copy of this project in your Posit Cloud workspace. Okay, so this looks and feels a lot like RStudio Desktop if you haven't used Posit Cloud before. And the project has all the packages already installed, and it has the two notebooks that we're going to work on today. So that's all it has. Go ahead and click on the first notebook. All right, so in your Files pane in RStudio, click on the AgroClimate Notebook 1 RMD, and it will open up in the source window in RStudio. And we're actually going to, we're going to work in visual mode today. So this is, RStudio has a visual editor. So click on the visual button in the toolbar of your notebook. And once you have this, people can put a thumbs up so that I can see that this is working. If you're behind or you're only half paying attention, this is a good time to keep watching us fine. This stuff is going to stay online for a while. Okay, so it looks like the majority of people have managed to open up this notebook, and we're working at it in in our Studio Cloud. Okay, so I'm just going to talk through and we're going to run through the code in this notebook from top to bottom and discuss it. You may have noticed I've closed my console. I've minimized it. We don't need it. I'm going to close this outline as well. And I won't read through every piece of this, but the idea that this will be your notebook that when we're done running it in about 20 minutes, you can save it. You'll have an HTML file that you can download, and then that'll be your notes for today's workshop. Okay, so this is what we're going to do in the notebook today. We're going to work with weather station data from the CIMIS network. So that's a government-run network of weather stations here in California. That is very popular. We'll import data from a single season, daily data, and a single weather station. We'll filter it based on dates. We'll make some plots. We'll compute a rolling average. It's one way to summarize stuff. Then we'll look at some of the threshold-based metrics, compute the last freeze state, which is something we worry about here in California or parts of the state, and so on and so forth. All right, so let's get on. I'm not going to read through everything, but go ahead, scroll down to code chunk number 1. You can see it in the gray box, and run the whole thing. So you can either click the little green arrow that says run code chunk. You can also click inside it and hit Control-Shift-Enter, and that will run all of the lines of code in that code chunk. Okay, so there is no output generated from this code chunk, so we can keep going because message equals false tells it we don't need to see the output. I would actually suggest at this point, click the save button, because what that's going to do, it's going to actually bring down some dependencies in the web that will be helpful later on. Okay, next, let's keep going down, scroll down. And the very first thing we're going to do in code chunk number 2 is we're going to work with the CIMIS network. So the CIMIS has an API. You can register for an API key on the CIMIS website. It's free. And then you can start using the API. And a very nice person wrote an R package for the CIMIS network. This was a former grad student at UC Davis who wrote this package. So please, it'd be good to check that out if you're interested. But we're going to be using his package to get CIMIS data into R. And the first thing we're going to do in code chunk number 2, go ahead and read code chunk number 2, is we're going to import the locations. There's about 150 of these weather stations. Now you might notice some of the lines of code in code chunk number 2 are commented out because we're not actually using the CIMIS because I'm assuming most of you don't have a CIMIS API key, and I didn't want to give everybody my API key. So we're just loading it. I've already done that, and we're loading it from the CSV file. But if you do get your CIMIS API key, you can uncomment those lines of code, paste in your API key, and then get them from the API. All right, but as you can see, we're only looking at, in the output of this code chunk, we're only looking at 6 of the roughly 150 weather stations out there. And you can actually scroll over and see the various columns that this function gives us about the weather stations. Okay, code chunk number 3, come down to code chunk number 3, and go ahead and run the whole thing. Click the little green arrow button. And let's talk about what's going on here. So what we got previously was a data frame. Stations all TBL is a data frame. And here in code chunk number 3, we are using some of those dplyr functions. First of all, we're saying only give us the ones where is active equals true, right? We only want active stations. Some of them are not active. The next line there, select, the select function, we're only getting 4, we're only keeping 4 of the roughly 15 columns that we got for the locations. So we don't need all of them. The next function there is distinct, and that is getting rid of some of the duplicates. For reasons I don't really understand. Well, some of the stations have duplicate records because maybe they were inactive at one point and then they became active. There's some different reasons why you have some duplicates, but that's the distinct function gives us back just the distinct copies. And then finally the transmute, it's a little bit like mutate. We are basically converting the longitude latitude coordinates from a comma separated into decimal degrees. Right? Don't need to understand every detail, but that's what code chunk number 3 is. We're cleaning up the location of the weather stations. Go ahead and run code chunk number 4. And what code chunk number 4 is, again, I'm not going to read through every piece of it, but it's basically taking that cleaned up data frame, making a simple feature data frame out of it, and using the SF package, which we loaded before, and then plotting that in leaflet. I'm not going to talk through this code in depth. It's not really a point of today's workshop, but you can zoom in and you can click on one of the little blue circles, and those are the locations of the active weather stations. Right. So this just illustrates how you can work with these kinds of data in R, including your maps. Okay. Code chunk number 5. Go ahead and run code chunk number 5. And what this is going to return, there we go. What this is going to return are the list of variables, the weather variables that you can get through the API from the CIMIS network. And you can tab through the different pages there. There's 43 of them. And it's the usual suspects, right? It's your wind speeds, precipitations, reference evapotranspiration, which we'll talk about, temperature, and so forth. And that second column, data item, that's the character string that you're going to use if you want that variable back in the next code chunk. So in the next code chunk number 6, we'll come down to code chunk number 6 and run it. And what we're doing here, you can look at the lines that are commented out because again, we don't have an API key for CIMIS loaded up. We're using the CIMIS data function from the CIMIS package, and you can see the arguments for it. It includes the number of one of the stations. We're using the Verona station, which is north of Sacramento. The items, those are the weather variables that we want to get back, and then the start date and the end date in a well-formatted character value. All right, so go ahead and run code chunk number 6 if you haven't already. And now we actually have some weather data for this station. And so we're getting all of the data from October 1st, 2021 through the end of September of this year. And we're getting the air temperature, the maximum and minimum air temperature, reference evaporation, transpiration, and precipitation. Right? So these are the 4 weather variables that we'll be working with for the rest of the notebook. Okay, great. Okay, so a couple things to note here about that data frame that we got back when we actually queried one of the weather stations. Note that it's in long format, right? So if I scroll over here, we can see the item column. So basically all of the variables, the precipitation, the evapotranspiration, they're all mixed together in one column. So that's something we'll have to deal with, right? It's as opposed to separate rows or separate columns. But that's a little bit of something we'll have to deal with. The date column though is formatted as a date object, so we don't have to convert that to a date object. There's a column called Julian, which is the numeric day of the year, 0 to 365. And QC is also a quality control flag. And there's a link there that will tell you what those values mean. Right? That's one of the things. Good weather station network will give you some measure of quality control. Okay, let's go to code chunk number 7. And let's start filtering out. So we got 365 days of data for 4 variables. But let's say we're only interested in the growing season, which we're going to define as April 15th through September 30th. So this is time filtering. This is pretty standard when you're working with weather data. So go ahead and run code chunk number 7. And you can just look at the dplyr expressions. It's pretty easy to figure out. We're using select to grab just 4 columns out of all the columns we downloaded. And then we're using the filter function to specify the dates that we want, right? Because that date column is formatted as a date object, the greater than or equals to and the less than or equal to, those work fine for filtering, right? And then we're looking at the first 20 rows. Okay, let's keep going down. So now we've filtered out a portion of our data based on the date. Go ahead and run code chunk number 8. And here we got we're just doing a little ggplot, right? It's always, I like to plot things just as a reality check. And we're plotting the maximum daily temperature for this smaller period of time that we've extracted, right? Okay, let's keep going. Come down to code chunk number 9. Here we're going to start working with rolling averages, right? So the rolling average, it's pretty intuitive. It basically takes a sliding window, in this case, of 5 days, and takes the average of there. So it's a way to smooth out time series data. Okay. So let's talk about how do we make that moving average. So let's talk through the first line of code chunk number 9, and we're using the mutate function. That's the function from dplyr that adds a column to a data frame, and we're defining that we're using the roll mean function from the zoo package, which does what it says. It generates a rolling mean from a column of numbers, in this case, the max temp column. K is simply the number of days it is, and then fill equals NA. That's important because the first couple rows and the last couple rows, there aren't enough to take a rolling average of length 5, so it has to pad those with NA values. Okay. Okay, so Prakash got an error message in chunk 8 when he ran chunk 8. The issue there almost always is going to be you forgot to run one of the code chunks above it. That's common when you're working with notebooks. And the trick there, Prakash, is that if you click the little button on a code chunk that says run all code chunks above it, it'll literally go from the top of the document and rerun everything down. So whatever you've missed, it'll get run. Right? So that's a good little trick if you get those things. But all of these code chunks have been I've tested, so they should all work. Okay, so we just created a rolling average. Rolling averages may or may not be helpful for agriculture. You kind of want to know the variations. But if you are looking for something like a heat event that lasts 3 days, 5 days, 7 days, 9 days, a rolling average is one way that you can see when there might have been a high spell of extreme or high heat. Okay, so I'm going to skip challenge 1, so we keep going, and let's come down to the next section of the notebook, which is about threshold methods. And this is where we're going to look for those days where one of the weather variables, in this case temperature, exceeds a threshold. This is a pretty common weather metric, frost days, tropical heat nights, heat days. All of these are threshold-based metrics based on a single variable, single weather variable. And they're easy to make in R. Or if you look at the code chunk 11, go ahead and run code chunk 11, and look at that mutate function. Basically, we're defining a new column, hot yn, and the expression is simply a conditional expression that will be true or false based on whether the value of max temp is greater than 100.4 or not. So the value of the threshold will depend on what the metric is. So 100.4 is defined by that's a bad thing for certain kinds of plants. Other kinds of metrics that threshold value might be based on the historical patterns at that location, right? So there's different types of thresholds depending on what the kind of metric is, but they're basically threshold values. Code chunk number 12, go ahead and run that. This is basically once you've created a column of true false values, which is based on a threshold. These are a couple expressions that you can use to count up the number of true values or the number of true values and false values using sum or table. And you can also plot those as well. So code chunk number 13, go ahead and run that. We're not using that true false column here, but we are just simply putting a horizontal line in our temperature plot to see where the temperature was over that red line. Right? So that's a visual way to kind of see where did you get those hot dates. Okay, let's keep going. Challenge questions, you guys can do those on your own. Let's now talk about the last spring freeze, because that's a problem. And there's different ways to measure freeze frost exposure, but we're going to use a simple one, which is basically where the daily temperature drops below 32 degrees Fahrenheit. Okay, so step one, so our job here is this data set. We want to find out when was the last frost day this year at this location. So code chunk number 15, go ahead and run code chunk number 15. And let's look at what it's doing. So we are filtering the data. We're only keeping the minimum air temperature rows, because you might remember what we downloaded had 4 variables combined. And we're only interested in this case in the minimum temperature. So that's the first piece of the filter expression. And then we have 2 date expressions to only look at the period from February through June for this data set. So that's what's going on there. And then that's followed by a mutate expression, where again, we're defining a new column called frost day, which is defined by a true false value if the value column is less than 32, and then we're doing a select, right? So now we have a frost day column, so we're almost there. Code chunk number 16, go ahead and run that. This will tell us in this February through June, there were 16 days at this site where the minimum temperature was below 32, and we want to know what was the last one. And that's what code chunk number 17 does. Go ahead and run code chunk 17. And you can see how we're using dplyr, right? So we're only keeping the days where the frost day was true. That's what we're interested in. And then we are arranging them by date in descending order. So we can see April 12th, 2022 was the last day of this season, or the season that just passed, where the temperature was below 32. And then code chunk number 18 is doing the same thing, but we're just adding on pull statement, pull out that column. All right. So that's an example where we are finding the date when the first or the last event occurred of a threshold metric. Right. So you can do a lot with that kind of stuff. Okay, but now let's talk about the next thing then. Is sometimes you're not interested in like 1 day of extreme heat or hot, but maybe 3 days or 2 days or 10 days. So those are referred to generally as a heat spell or a heat run. And let's think about how we can pull those out in R. And what we can use here is a function from base R called RLE, stands for run length encoding. And code chunk number 19 will show you what it does. So go ahead and run code chunk number 19. This is illustrating what this RLE function does. So what you do is you pass it a vector. In this case, it's a vector of letters. But soon it'll be a vector of true false values. And what this function gives you back is a list. And the list has 2 elements. And each of the items of those 2 elements represent a group of repeated letters in this case. So the length element tells you the number of, in that group, the number of elements. And then the values element tells you, the value of that element, right? And with these two things, you can basically recreate the original vector. That's kind of what the purpose of this function is to kind of compress based on linear repetitions. But you can see how that would be useful in working if you're looking for spells of threshold values. So code chunk number 20, we'll use that to shows us, like, it will answer the question, how many groups of letters were of length 3 or greater, right? So we're, again, defining a conditional expression, length is greater than 3, and then adding those up, which will give us the number of trues. So it means in that pattern of letters, there were 4 groups that had 3 or more letters. Soon this is going to be the number of consecutive hot days. And then code chunk number 21, you could run that, is doing another kind of summary of those groups of 3. It's telling us for those that were 3 days or more, what was their average length? Okay. And then code chunk number 22, I'm not gonna, this may not be intuitive, so don't, you may have to wrap your head around how these expressions are working. But code chunk number 22 is we're applying 2 conditions, right? We're saying we want to know specifically groups of the letter A repeated that are more than 3 or more occurrences. How many of those did we get, right? So we're using a composite conditional expression. Okay, so applying that now not to letters, but to our hot days, run code chunk number 23. And this is where we're taking that column of true false values that said that was a hot day, and we're applying that RLE function to pull out the repeated groups in there. And then finally in code chunk number 24, we're getting the answer is there were 4 groups of consecutive days where the temperature, consecutive days of 3 or more days where the temperature was over 100. Right? You don't get every detail. It's okay. This is probably the kind of thing you'd have to come back to, but it's possible, right? You can find these runs and come up with different submits. Okay, let's keep going. I don't see any questions, so we'll keep on going. So let's talk about, so those were some simple metrics based on a single column at temperature. But there's some other metrics where you may need to work with, 2 or more weather variables, such as the maximum temperature and the minimum temperature. So it's generally easier to compute metrics that involve, as the raw ingredients, more than one column of the weather variables if they are in separate columns. And that's not what we have right now. They're all in one column. So go ahead and run code chunk number 25. And this is just to remind us of what we got from CIMIS, right? So we're picking 4 of the columns. And you can see all of the variables are on top of each other. But code chunk number 26, this is where we do a little magic. So if you look at code chunk number 26, we are, first of all, filtering what we got down, keeping only the 2 variables of interest, in this case, the min and max temperatures. That is followed by a select statement. So now we're just keeping 3 of the columns. And then that is followed by a pivot wider function. And that's from the tidyr package. And that does the splitting. And we don't really have time to go into all of the arguments for pivot wider, but you can more or less, you should be more or less be able to follow what it's doing. It's like doing a crosstab query or a pivot table. All right. So that's an example of taking your data and splitting it across multiple columns. Now that we have it in multiple columns, come down to code chunk number 27, and it's easy peasy to compute the average daily temperature. You use mutate, you define, you type in there a little equation that generates the average based on the min and the max. And then code chunk 28 is another very simple formula. The diurnal temperature range, which is a real metric that's useful, is simply maximum temperature minus the minimum temperature. Right? So that's what those give us. All right. Code chunk 29 is plotting that diurnal temperature range. And you can see it varies quite a bit. So basically the Y bar there, the Y axis here, that's like how much the temperature varied in a single day. And there are some days where it varied by over 50 degrees. That's pretty extreme. Those might be days when a cold front or a warm front is coming through, and so on and so forth. And there seems to be a seasonal pattern too, where you see swings of temperature. And that's going to depend on a lot of stuff at this location. Okay, so code chunk number 30 is the same. All right, let's go down to any questions here. All right, thank you, Shane, for getting into the nitty-gritty of projection systems. I'm going to keep going, and let's talk about evapotranspiration, because this is a really useful metric for irrigators, which is most people. So the concept here is that with precision irrigation, you just want to replace the amount of water that the crop has lost since its last irrigation. In essence, that's what it is. And the water that has been lost is going to be the evapotranspiration. So that's off the plants, off the leaves of the plants. And then evaporation, which is like from everything else, primarily the soil, right? So those are the two types of water loss that evapotranspiration combines: transpiration and respiration, or evaporation and respiration. Now, how do we figure that out? So these weather stations report, the CIMIS weather stations at least, report reference evapotranspiration. And because what plants respire will be different for different types of plants in the different growth stage. So the idea is you take that reference evapotranspiration from the weather station and you multiply it by a number which is specific to your crop, say it's celery or tomatoes, and as well as the specific stage of the crop. And then that tells you how much was evapotranspirated on that day. And then you subtract, so that's the amount of evapotranspiration. If there was any precipitation, you have to subtract that out. And then the balance is the amount of water that needs to be replenished per day. There's a lot more details into it. There's a couple links you can click on, but run code chunk number 31. And let's look at code chunk number 31. So we're starting with the data we got from CIMIS. We're just keeping the reference ETO and the daily precipitation because that's what we need to do this calculation. Throwing it, we don't care about the daily min and max temperature. And then we're pivot widening those, so now they're in separate columns. So that's code chunk number 31. And then code chunk number 32 is where we're going to compute the crop evapotranspiration, in this case tomatoes, based on a crop coefficient, which some researchers cooked up. That's KC. And what code chunk 32 gives us now is a day by day, the amount of total water that was lost due to evapotranspiration. So we're almost there. The only thing we need to factor in, though, is any precipitation that occurred. So come down to code chunk 33. And if you look at the mutate function in code chunk 33, that's where we're taking that evapotranspiration from the tomato plants, subtracting out precipitation, which was 0 for most of the days, but there were a few days where there was some precipitation. And that gives you your net water loss for that day. And then code chunk 34 is where you say, okay, now we know how much it lost each day. Let's say I irrigated it on June 10th. Today's June 15th. How much water do I need to put back on there? And that's what we get, right? So that's pretty quick, but that's basically the work. That's pretty simple, right? You figure out your daily evapotranspiration, subtract out any rain, and add those up since the last time it was fully irrigated, and that's how much water you need to put back. I mean, that's really simplified, but that's essence of precision irrigation using this technique. Let's take a 5-minute break. We'll resume at 12:15, 15 minutes past the hour. Okay, so next, I'll start part 2. And in part 2, we're going to talk a little bit about somewhat more complex agroclimate metrics and how some ways to summarize in our multiple years of data. Okay, so let's talk about degree days, because it's one of the most common, one of the most useful metrics out there. So in broad terms, this is the background of degree days as a metric is that plants and insects are cold-blooded, they're poikilothermic, meaning their metabolic rate, the cell division and all the little processes that in their physiology the rate varies a lot with the ambient temperature. Other things as well, water, nutrients, of course, but all things being equal, temperature is a big factor that in some ways it helps us predict their rate of development because there is such a strong correlation. In addition to that, it's not just correlated linearly with temperature, like all the way down to to zero. All organisms, their internal temperature needs to be above a certain threshold. Otherwise, things just kind of stop and they go into cold freeze down mode, or they just go into dormancy, or stop developing. And then likewise, there's also an upper threshold, right? So within a range of temperatures, that's the physiology of plants and insects is designed to run. So that's kind of the underlying basis of degree days. And phenology events, when you can actually visibly see a difference, such as things are blooming, hulls are splitting, eggs are being laid. These events can be correlated with an accumulation of the sum of warmth within that usable temperature range. And that is the essence of what a degree day is. I mean, that's not the definition of a degree day, but the essence of it is that the timing of growth and phenology events is well correlated with the total amount of warmth within that usable range, right? And that's why calendar dates generally are not too reliable for predicting when things will be ready or how things quickly will grow, right? So that's kind of the science behind it. Now from there, and we also know, okay, well, we have temperature data. We definitely have daily min and max temperature data, a lot of that. We don't have as much hourly data, at least it's not that easy to find. But you can compute the degree days from daily min and max with mathematical equations or models. There's different ways that you can model the total amount of warmth, or there's different ways that you can model how temperature changes from the minimum to the maximum within a day. I'm not going to talk through this, but suffice to say, researchers have been studying this for a few decades, so it's fairly well dialed in. There's these different methods. The mathematics, though, are not trivial. So this is not something you can do in a couple lines of dplyr, right? So these methods, because you also have to take into consideration not just how temperature varies over the course of the day, but also what portion of that temperature is between those upper and lower thresholds that are specific for species. So the calculations are a little bit gnarly. Fortunately, though, there's a degree day package authored by yours truly that takes these equations and makes them into user-friendly R functions. And my colleague Shane Fryer, who's on here, has developed a similar package for library for Python. There's a few other places too that have these equations coded up, but these are two good ones. So degree days, they're useful. They've been used by researchers for many decades. They're well studied. They're not really that useful by themselves, though. Generally, they're useful in combination with some kind of phenology table for a specific plant or specific species of insects or pest crop combo that predicts when different things are going to take place based on the accumulated degree days. So you really do need phenology tables to help you. And then those phenology tables will also tell you when you should start counting, right? Because this goes on continuously. But the researchers who did the field work to find out how long it takes for eggs to happen or for the hulls to reach their maximum volume, they kept track, and then the phenology tables will tell you when to start counting, which is generally called biofix. This is sometimes called, or sometimes this is just a standard calendar date, like January 1st, start counting. More often though, it's when you observe something in your field, right? Or your neighbors observe things around you, right? So it's an observed event, right? So, but the combination of phenology tables with the biofix plus degree days can give you some good predictions. And we're going to be looking at doing that next in our next book. A similar concept is chill. So chill hours and chill portions measure the net accumulated amount of coldness that a tree is exposed. Now you might think, well, why is that useful to know? Right? Degree days, you can kind of understand temperature is correlated with growth, but fruit and nut trees have an interesting adaptation to prevent them from being nailed by frost. And they have some way of keeping track of the cold that they experience over the winter. And that tells them when it's winter's over and it's time to start, sending the sap up to the flowers and making buds and all the rest, right? So chill hours are useful and chill portions are useful because they mirror this mechanism that trees have developed. And basically they can tell you when your trees will start coming out of their winter dormancy. There's two ways to measure chill. Chill hours are simply a lot like degree days. It's simply the number of hours that are below a certain threshold. I think it's 7.5 centigrade. Might be off there. Chill portions, though, are another technique of counting up chill. It's more complicated. We can't get into the details here. Oh, 7.2, I can't even know. But they do a better job at predicting spring. They do a better job at mimicking how trees internally keep track of chill and come out of dormancy. So fortunately, Dr. Ike Ludeling here, who's with us, he's the expert on this. He's got a great ebook on phenology analysis for trees in R, and he's the author of the Chill R package that we will be using. All right, oops. So there's a lot of details, but that's the essence of it. Right? Okay, so in the next notebook, we're going to be working with degree days and chill portions. And we're going to be using the specialized R package to compute those and then use our dplyr functions to visualize them and get the data ready. So a couple of things that we're going to be using here, because we're going to be working with multi-year data. So we are going to be filtering the weather data to certain times of the year. But we can't use dates because we have multiple years of data. So we're going to be using date parts, right? And so basically we're going to be adding columns to our weather data frame for the month, the year, the Julian day, and so on and so forth, right? This is pretty standard. It's pretty easy to do. The function that we're going to be using is called, the package that we'll be using to add these columns is lubridate, which is one of the tidyverse packages, and has these little functions. You give it a date object, it'll spit out the day of the month, the year, or the Julian date. All right, so we'll be using that. Another package that we'll be using coming up is the units package. And this makes it really easy to convert numbers between units. Because a lot of times you might get weather data and it's in Kelvin or centigrade and you need it in Fahrenheit or vice versa. So this units package has a database, lots and lots of constants, and you can change between units with the set units function without having to look up your conversion concept. All right. So we'll be using the units package. We will also be wanting, because we're working with multiple years of data now, and we want to do summaries of that time period, we're going to be grouping and summarizing the results with dplyr functions. And specifically, we'll be using the group by function from dplyr, which kind of invisibly defines groups of rows in a data frame. And then we'll feed that data frame into summarize. And this is the function where we can put in functions that will create columns for each group of row that will calculate the mean or the median or the first or the range, all your typical aggregate functions, all right? So we'll see a lot of examples of this kind of using group by followed by summarize, right? So that's a really common combo in working with data frame data using dplyr and tidyr, okay? So here's an example where we're doing just that. We have the storms data frame, which comes with dplyr. We're selecting and filtering, and then we're using group by. And then so for each group of months, this is a multi-year data frame of storm events. We're calculating N will give you the number of rows in each group, right? So we'll see examples of this. But it's a very handy way to kind of create these row summaries. Okay, so let's go into RStudio. Any questions here? All right, very good. Okay, so go back to RStudio. I'm going to close notebook 1. Your RStudio may have gone to sleep, in which case just wake it up. And go ahead and open up the second notebook. So go into RStudio, Cloud, pause the cloud, and open up the second notebook and go into visual editing mode. You don't have to. I'm going to go into visual mode. I'm starting to like this. And then we'll get going. The other thing I'm going to do, which is generally good practice working with R in RStudio, is to restart my R session. So I'm going to go to session, the session menu, and restart R. One of the reasons for using notebooks and working in notebooks is that your work is completely reproducible or should be reproducible. So by restarting R, it makes sure that all the code is going to work. It also will help you in the RStudio cloud environment manage memory, right? So all the variables that we had before will be gone now. Okay, so we are in notebook number 2. I'm going to keep going here. Please chime in if there's a problem. What we're going to do in this notebook is we are going to work with 10 years of daily data at this point. And we're not going to use CIMIS. We could use CIMIS, but we're going to use gridMET. So gridMET is one of those interpolated data surfaces, weather data surfaces. And it's based on PRISM. I think the resolution is 4 kilometers. And it's basically PRISM, and then you do some additional processing. And one of the reasons I'm using it, to be honest, is because it's on CalAdapt, or up through 2020, CalAdapt. And there's an API package for CalAdapt. So we'll grab a lot of daily data from gridMET. We'll use the units package to do some conversions. We'll time slice it to come up with certain, just the cold season or just the growing season. And then we'll compute the degree days and chill portions. All right. So go ahead and run code chunk number 1. If you're still with me and following along, code chunk number 1, we're simply loading up a few packages. Code chunk number 2, go ahead and run code chunk number 2. Here we are using the CalAdapt R package, and there's a whole series of notebooks on there. I've seen this before, this little yellow bar. If you save it and then run it again. Okay, I'm going to do, if you're getting this little yellow message, the other thing you can do is clear your cache. All right, so if you're getting the little yellow bar about a dependency not found, clear your knitr cache. So click the preview button in the toolbar and choose clear knitr cache. And then try running code chunk number 2 again. Let me try clearing all output. Okay. So the two things, if you're getting that little yellow, this is an RStudio Cloud glitch. If you clear all your output and also clear your knitr cache, and then it should work. Or you can just close that little error message. It's not a deal breaker. Okay, code chunk number 2. We are searching the CalAdapt API data catalog for the data sets, for the gridMET data sets. Right? So CalAdapt is a portal of climate data for here in California and the West Coast. And you can use this function from the CalAdapt R package to see there's like over 950 data sets. So it's a big data source. But we can see the layers that have the word gridMET in them. And what we're looking for here is daily temperature data. And what we need the slug. So the slug is what you see as the name of each. The slug is like a unique identifier for each data set. All right. So that just kind of explains, you can see Tmin, day, gridMET. That's going to be one of the ones that we get. Some of these are already summarized by year. We're interested in the daily data, and we're interested in minimum and maximum temperature. Okay, so with that being said, code chunk number 3, go ahead and run code chunk number 3. What we're creating here, again, this is all stuff from the CalAdapt R package, so you don't have to know the details. But basically what we're creating here with these functions from that package is we're creating an API request object. We haven't actually gotten any data yet, but we're creating the object that we're going to send to get some data. All right, so that's what PT1_CAP, that's what that is. That object is an API request object. You can plot it if you want in code chunk number 4. And when you plot an API request object, it shows you where the location is in that request. There's a whole series of tutorials on this package if you're interested in learning more. And then code chunk number 5 is where we're actually getting the data. And again, we're cheating here a little bit. We are grabbing a copy of the data that I downloaded a few days ago, as opposed, but if you uncommented the code chunk number 5, if you uncommented the commented line, that actually would communicate with the CalAdapt server. And that should work because it doesn't require registration or an API key. Okay, but now code chunk number 5, we have some daily data, and you can see how many. It's got 7,300 rows, so 10 years of data for 2 climate variables. And this is observed data, right? So if this was future data, there'd be models and emission scenarios and so forth, but we're just dealing with daily observed data. Okay, so code chunk number 6, go ahead and run that. And we're basically taking what we got from the CalAdapt server, and you can see what the mutate function is adding here. We are creating a date column, and we are creating a temperature column, right? So this data frame that we're dealing with here, it's also in long format, so it has the minimum and maximum daily temperatures combined in one data frame. But now they are in Fahrenheit. So we're using, they come down in Kelvin. I'm not sure why. Well, actually with the gridMET, it may not come down in Kelvin. And the other stuff it comes in. Oh, it is in Kelvin. Yeah, see, why does it, I don't know, I guess scientists like Kelvin. Okay, so that's code chunk number 6. Code chunk number 7, run that if you haven't already. And this is a plot of this 10 years of daily data. And you can see the ggplot syntax there. We're basically plotting minimum and maximum temperature as 2 different facets. Okay, and it looks like what it should look like. Okay, so an important note here is that gridMET is model data. It's interpolated data from weather stations, but they've already dealt with missing values, or like the data logger was not working or something happened. This is a benefit of working with modeled data. But if this was CIMIS or any other weather source, our next step right now would be to look for missing values or NA values. And then we'd have to fix those through substitution or interpolation. So we don't have to do that. In the real world, you probably do have to do that. Ike has a really nice chapter in his ebook on different ways that you can deal with missing data. So there's a link to that. Okay, now we have 10 years of daily data. So code chunk number 8, go ahead and run that. And what are we doing here? Well, we're adding in those date parts, right? Because we're going to look, we're not interested in 12 months of the year. We're interested in just the growing season or just the cold season. So we're adding in columns for the month and the year. All right, so that's what's going on in code chunk number 8. Nothing else fancy is going on there. Code chunk number 9, let's do some basic statistics, descriptive stats for the 10 years of data. So code chunk number 9, you can run that. And as you can see, it's using group by followed by summarize. So we're pulling out just the maximum daily temperature, and then we're grouping those by year. Now, these are calendar years, not agricultural seasons. And then for each group, we're computing the mean daily temperature, right? So that's what that little table gives you back. Okay. So that's code chunk number 9. So that by itself could be a useful summary. Code chunk number 10, go ahead and run code chunk number 10. This is an actual metric that's been used by researchers. In this case, the average high temperature for the month of July has been shown by tree researchers to be a good measure of the maximum amount of heat stress that trees can survive. So this has been used by McBride and Lacan. They were, in their paper, they were asking, and for urban trees, like what should we expect to be survivable in the coming decades? So they did this climate analog study using this single metric, right? So for every location, what was the average daily temperature in the month of July? And that becomes the metric for the trees that can survive at that location. All right. Okay, so code chunk number 11 is doing the same thing, but you can just see we've taken out the group by. So now we're still using summarize, but without the group by, it's summarizing all of the rows. So this is getting for the entire data set for the month of July, because the month of July is being used as a filter. That's the, so this 94.7 degrees Fahrenheit, this would be a good measure, a reasonable measure of heat stress relative to trees for this location for this 10 years of data. And then you can compare this to the expected highs at the end of the century to see what that's going to look like. Okay, questions? Okay, let's keep going. Next, so that's working with like months, like the month of July. But a lot of times you want to work with like a custom time period. So that's what we're going to do next. We're going to add some columns for custom time periods. One of custom time period that's used quite a lot is the water year, which is defined as starting on October 1st. That's when like rains will start to come for the next 12 months. So in code chunk number 12, go ahead and run code chunk number 12. We are adding a column for the water year. And basically, as you can see, it's simply the calendar year. And then if the date falls in October, November, or December, then you add 1 because the water year number should be the end of the water year, right? So October 2020 falls in the 2021 water year, right? So code chunk number 12, that's what we're doing. We're adding a column using the if-else function from dplyr. That's a vectorized function, so it works in mutated expressions. So that's one way that you can tag dates, individual dates, to a custom time period. And run code chunk number 13. Here we're defining the, here we're interested in pulling out just the dates from April 15th to June 15th, right? This is a time period, it's critical for a certain crop or a certain pest. And we want to grab it for every 10 years. So in this case, we're using Julian dates. So the Julian date for April 15th is 105. So that's 105th day of the year. We calculate the Julian date for June 15th, that's 106. And then we use those numbers in a filter expression from dplyr. And what we're left with are just those, just the values for those days, right? Just the records for those days. All right, so you can almost always use Julian dates for any crazy custom time slice that you want to use for multiple years of data. Right? Okay, and then what are we doing? Code chunk number 14, we're simply taking that time slice from April 15th to June 15th, that filtered data set, and then we're making these box and whiskers plots over the 10 years, right? So you can see the key thing there that makes the box and whiskers plots for each year is in the ggplot statement, we're using group equals year, because the geom box, the box plot geom function will look for groups of data and make separate box plots for each of those. Okay, let's get now down to degree days. Okay, so coming now, we've already talked about degree days. They're basically accumulated measures of temperatures within different range using fancy equations. So let's look at degree days for navel orange worms. And there's 2 steps again. First of all, we calculate what is for every day, what is the number of degree days for navel orange worms, specifically in almond orchards. And then we're gonna, that by itself isn't very useful. We have to combine that with a phenology table that tells us how many degree days it takes for things to happen, which we look up on the web. There is no easy, simple source for phenology tables. That's a side project of mine if anyone's interested in helping me understand, putting together something that's more structured and machine readable. I'll keep working on that. Okay, code chunk number 15 is going to, you can see what's going on here. We're simply getting ready to compute degree days. And to do that, we need to have the minimum and maximum temperatures as separate columns. So you can see that pivot wider function there. So that's what's happening in code chunk number 15. And it looks like we're using the entire 10 years of data. And so we're going back to what we got from gridMET. Code chunk number 16, scroll down and run there. And this is where we are loading up the degree day package. We are telling it what is that lower and upper temperature thresholds. And then we're using functions from that package to compute the degree days specific for navel orange worms using the single sign method, which is what is recommended for this insect. Right. So at the end of that, we now have a column in our data frame, which are the number of degree days for every row, for every day in our 10-year data frame that can be used by navel orange worms for growth. Okay, so that's the basis, but we haven't done anything useful quite yet, but we're ready to do that. In code chunk number 17, we are going to examine how we could use the degree days to time different things. So go ahead and run code chunk number 17. So as you can see here, we're pretending that there was a biofix event on April 18th, 2011, right? So one of the biofixes for navel orangeworms is when you start to see eggs on your traps over multiple days of a pattern of increasing number of eggs on your traps is a biofix event. So we are using the filter function from dplyr to only grab days after April 18th through the end of that season. And notice also we are using in the mutate statement the cumulative sum, cum sum function, because that's when now we want to start counting them up. Previously, we weren't counting them up, but now that we have a biofix state, we can start counting them up. So you can see that column in our data frame. So now it's easy. We want to know after April 18th, when did we accumulate 100 degree days? That's code chunk number 18, right? It was May 4th, right? So the IPM website says, if you want to spray, maybe the eggs start to hatch and the little worms are vulnerable. That's a good time to spray when 100 degree days have accumulated. That's when you would expect these eggs to hatch. That's what the pest management guidelines are. And code chunk number 19 computes another phenology event, also based on the research from the phenology table. And that one says 1,056 degree days after your last biofix event, you could expect to see the next generation of adults. Right? So that's just a couple examples of using the numbers from the phenology table with actual data and coming up with some useful results for a specific season. Code chunk number 20 is a different use case. Here we are estimating a biofix when we don't have observations. So if you don't know when when navel orangeworms first emerge, a good estimate based on historical research is after 300 degree days have accumulated since January 1st, right? And for this historic period, maybe we did, maybe we didn't have observable data, but definitely if you're doing projected climate studies, you're not going to have observed data. So this is the best guess of, if you're interested in how navel orangeworms are going to change over in the coming decades, this could be a technique that you can use to come up with your first biofix event. Right? So that's what's going on in chunk number 20. I won't talk through the whole thing, but basically you can read through it. And for every year, we are computing, we are starting to count. I should note something here, though, that's an important trick that you can do with dplyr is you can see the group by statement in chunk 20 after we've done where we're grouping by year, and then we're following that with mutate. Normally, after group by, you put summarize, but here we're putting in mutate. So when you have mutate followed by after a group by statement in the dplyr context, it's going to mutate. It's going to create that column, and it's going to evaluate the column values for every individual group. And that's exactly what we want here, right? We don't want the cumulative sum of degree days from 2011 to 2020. We want it for, for the beginning of each year, group by the January 1st. Right, so you can use mutate after group by for this kind of work. And then code chunk 21, go ahead and run that if you haven't already. And this is simply doing a simple little filter expression followed by a simple little summarize function to tell us when do you see 300 degree days first accumulate for each of the years in our data set. Okay, let's keep going. So next, some of the other functions for computing degree days use the daily minimum and maximum temperature, but then you also need tomorrow's minimum temperature because it uses tomorrow's minimum temperature to model how the temperature changes over the second half of the day. Right? So that's the double sign, the double triangle methods. So code chunk number 22 and code chunk number 23 is where we add tomorrow's temperature. And what are we using? We're using the lead function, right? So the lead function from dplyr does kind of like a row offset thing. And you can kind of see the results. We are indeed grabbing the minimum temperature from the next day and using it as, and calling it as tmin next. And if you look at code chunk 24, you can see at the very end of the time series, it has to throw in an NA value. So you will get NA values if you use lead or lag, those offset functions, right? But they're useful, right? This is a good use case where you can add columns that are offset from other rows. And then now code chunk 25, we are using the double sign method from the gridMET package. And you can actually see the arguments that we feed. It includes the minimum temperature for the next day. And now we get another column of degree days based on that temperature. And you might wonder, well, which method should I use? Does double sign seems like it should be more accurate? The idea is you use whatever ones the researchers use, because you're trying to pair up your degree day calculations with what they did in their studies when they made, because the product of their work were these phenology tables, right? To get the value of their research. Okay, excellent. All right, we'll keep on going here. So next, we've been talking about, so far we've only been working with daily min-max data. Getting to chill now, we're going to have to, chill really does need hourly data, right? So you might have hourly data if you're having a weather station. If you are stuck with working with daily min and max temperature, next we're going to see how you can interpolate hourly temperatures from minimum and maximum. And the technique that we're using is from Minville 1990. And thanks to Ike, who's still with us, he has coded this up in his CHILL-R package. So if you run code chunk number 26, we are basically getting our data frame from gridMET. We're getting it ready to feed into the make hourly temps function that does that interpolation from the CHILL-R package. All right, but code chunk number 26, we're just putting the columns, we're putting the variables in separate columns. And then code chunk 27 is doing some more manipulations where we're making columns and we're giving them the right names. So everything, so now we have a data frame in code chunk 27 that's ready to go. And code chunk 28, this is where we are loading up the CHILL-R package. We're feeding in that cleaned up data frame and it's interpolating the hourly temperatures. Note also the other argument though that we're feeding to make hourly's temps, we're giving it a latitude value of this location. And the reason for that is because one of the Linville technique estimates the middle of the day based on the sunrise to sunset, and it figures out sunrise and sunset times based on the latitude. So that's why you have to give it a latitude value. Okay? But it's pretty easy to do. Right? So now the end result of that are going to be the hourly temperatures. You can see the extra rows that are in the result. And that's great. We could work with that. But we're in the next, in code chunk 29, we're actually going to take that wide format and then go back to a long format, because chill portions, we went to long format. All right, so that's what code chunk number 29 does. I think this is the first time we've seen today going from wide to long. Mostly we've been going from long to wide. There is actually a function in the CHILL-R package that will give you back your hourly temperatures in a long format. I was having some hiccup with it, but this does the same thing. Yeah, thank you. Each stack hourly temps can do the same thing. But if that gives you trouble, you can use pivot longer from tidyr. It does the same thing. Okay, so let's code chunk number 30. You might be curious, does this really work? code chunk number 30 actually plots the interpolated hourly temperatures for 1 week of our data set. And you can kind of see how it works. The first half of the day is modeled based on a sine curve, which is kind of like how temperature warms up. And then the second half of the day is modeled as a logarithmic decay of temperature until the next night. Okay, so now we have hourly temperature data. Yay, we can compute chill portions. So that's what code chunk number 31 does. Go ahead and click on there. And first thing that we're doing here, again, we're getting our data ready. Okay, so we are basically the chill portions function that we're going to use once the data, temperature data in Celsius, not Fahrenheit. So that's basically what code chunk 31 is doing. We're doing a little mutate there to get convert it to centigrade. And now code chunk 32 is where you can see we're calling the dynamic model, the chiller package, and it is computing for Naval Orange, it's computing the chill portions method. And we now have that column added to the data frame. And these are cumulative chill portions too, right? So the dynamic model function gives you the option to compute cumulative chill portions, which is usually what you're interested in anyway. You could do it, you could not have it do cumulative, but the default is cumulative. And then code chunk 33, our last code of the day, actually will plot those chill portions for 1 year of the data. And yeah, it looks like you would expect, right? So it starts getting cold, like late November, early December, and then goes up in there. And then each tree, you can look up the tree that would, for each tree species, you can look at how many chill portions are needed before it's going to wake up from its dormancy. Okay, well, that was a mouthful, but thank you everyone for sticking with it. Hopefully this was useful to you. Hopefully you saw that AgroClimate metrics are handy. They're useful for research. They're useful for farm operations. They're really useful for climate change impacts if you're looking at modeled climate data. And you can do lots and lots of this stuff right within R, and it takes a little practice, but it gets it's all quite doable.